Or it's November of 2025 and a crew of astronauts is finally wrapping up their mission aboard their space station, packing up, running through their checklists, getting ready to undock and head home. And then, out of nowhere, something stops the entire operation cold. Someone notices tiny cracks running through the window of their spacecraft. Not a manufacturing flaw, not ordinary wear from months in orbit. An impact, a strike from a piece of debris tearing through space at thousands of miles an hour. In an instant, that spacecraft, their ride home, is declared unsafe to fly. Those astronauts were effectively stranded, hundreds of miles above the Earth, and it took an emergency rescue launch to finally bring them home safely. The first time a mission like that had ever been required in that country's entire human spaceflight history. Sit with that for a second. An entire crew's homecoming derailed, a rocket rushed onto the pad and launched under pressure, all because of a run-in with a piece of space junk. That alone should be enough to make you sit up straighter. And here's the part that really gets under your skin. Whatever struck that window was almost certainly just one tiny fragment plucked from an estimated pool of 140 million pieces of debris currently orbiting our planet right now. This isn't science fiction. This is the actual state of the space surrounding Earth today, a space that is far more crowded, far more hazardous, and deteriorating far faster than most of us have ever stopped to consider. So that's what we're digging into. Why the people who study this for a living are genuinely alarmed, and what any of it actually means for those of us living our lives safely on solid ground. No manufactured panic, no doom just for the sake of clicks, just the real figures, the real events, and the science as it actually stands. Because honestly, the truth here is unsettling enough without any embellishment. Let's start with scale, because the raw numbers are the foundation everything else builds on, and they are staggering on their own. As of early 2026, researchers estimate more than 140 million individual pieces of debris are currently circling the planet. Let that figure actually land, 140 million. Now, the overwhelming majority of that is made up of tiny specks, flecks of paint, stray bolts, shards of shattered metal, fragments smaller than a single centimeter across. But mixed in with all of that are the much bigger, much scarier pieces too. Dead, defunct satellites that stopped functioning long ago and abandoned rocket stages, the discarded upper portions of launch vehicles, some of them the size of a city bus. When you narrow it down to objects large enough to actually be tracked from the ground, space agencies are now cataloging upward of 40,000 of them, a record-breaking number that continues to climb month after month. And sharing that same increasingly crowded volume of space are the roughly 14,000 functioning satellites that quietly power huge chunks of modern life. Now, here's the piece of the puzzle that changes everything. It comes down to a single word: speed. Objects in low Earth orbit are hurtling along at speeds beyond 17,000 miles per hour. At velocities like that, even a stray fleck of paint carries a genuinely shocking amount of kinetic energy, enough to pit, chip, and damage a spacecraft's surface. A fragment no bigger than a marble strikes with roughly the force of a fired bullet. And something the size of a baseball could obliterate a functioning satellite outright, or tear a catastrophic hole straight through something like the International Space Station. This is the mental shift you have to make to really understand this problem. Up there, size stops being the thing that determines danger the way it does down here on the ground. Speed is what turns even the smallest, most harmless-looking scrap of debris into something lethal. That cracked spacecraft window I mentioned at the top was almost certainly caused by something quite small, but moving fast enough to put an entire crew's lives at risk. To really understand why, it helps to think through the physics for a second. The energy carried by a moving object doesn't scale up in a simple straight line with its speed, it climbs with the square of that speed. Double the velocity, and you don't just double the impact energy, you quadruple it. And these aren't objects cruising along at highway speeds, they're moving at something like 10 times the velocity of a rifle bullet. When two objects on a collision course in orbit meet head-on, their combined closing speed can reach tens of thousands of miles per hour. At that kind of velocity, a collision isn't remotely like two cars gently bumping fenders, it's closer to a detonation. Both the impacting fragment and whatever it hits essentially vaporize and shatter apart, releasing energy comparable to a small explosive charge and spraying a brand new cloud of high-speed shrapnel out in every direction. That's the mechanism behind how a fleck of paint can crater a window and how one lost bolt can be enough to kill an entire satellite. Up in orbit, everything behaves like a bullet, and even the tiniest scrap of debris hits with a punch far out of proportion to its size. And nearly all of this chaos is packed into one specific region, low Earth orbit, the band of space stretching out to roughly 2,000 kilometers above the surface. That band happens to be the single most valuable stretch of real estate in all of space. It's where the International Space Station lives, where the majority of Earth imaging and communication satellites operate, and increasingly where massive new satellite fleets are being deployed by the thousands. It is, put simply, the busiest, most congested neighborhood above our heads, and it's exactly where all this junk is piling up the fastest. Here's a detail that makes the whole picture even more unsettling. That figure of 40,000 tracked objects only accounts for the debris large enough for us to actually see and follow. Go back to that estimate of 140 million total fragments and do the simple math. And what you find is that the vast, overwhelming majority of debris, tens of millions of fragments ranging from a single millimeter up to 10 centimeters across, is essentially invisible to us. We can't see it. We can't catalog it. We have no way to warn a satellite operator that one of these fragments is on a collision course. It amounts to an invisible, sprawling cloud of shrapnel silently circling the planet. And any single one of those unseen fragments moving at orbital velocity is fully capable of disabling or outright destroying a satellite on contact. So, when operators carefully maneuver their satellites out of the way to avoid a collision, they're only ever dodging the threats they can actually detect. The much larger population of debris, the swarm we're essentially blind to, keeps a silent game of Russian roulette running above our heads every second of every day. That cracked window on the spacecraft was almost certainly the work of exactly one of these invisible bullets, something so small it never once showed up on any tracking screen. So the current state of things is already crowded and already dangerous. But here's the part that really matters. The part this whole story hinges on. It's getting worse, and it's getting worse fast. According to the European Space Agency's most recent annual assessment of the orbital environment, the risk of a debris collision in low Earth orbit has climbed 20% in just the span since 2024. 20% in roughly 2 years. That is not a slow, gradual drift. That's a genuinely rapid acceleration of the danger. And the people studying this point to a handful of specific culprits driving that spike. The first is the rise of mega constellations. In recent years, companies have started launching satellites not in small handfuls, but in massive networks numbering in the tens of thousands, all designed to blanket the entire planet in internet coverage. That shift has caused the total count of active satellites to explode upward. And while these constellations genuinely do provide valuable services to people on the ground, they also dramatically increase how densely packed orbit has become. More satellites up there means more potential collisions, more objects that need tracking, and more opportunities for something to eventually go wrong. The second driver is deliberate intentional destruction, specifically anti-satellite weapons testing. Over the years, several nations have tested this kind of weapon by literally blowing up their own satellites while in orbit. Each and every one of these tests is an environmental disaster for the space around our planet. Destroying a satellite doesn't make it vanish. It shatters it into thousands upon thousands of brand new fragments, every single one a fresh, high-speed hazard, and a large share of them end up scattered into orbits where they'll linger for years, even decades, before finally coming down. Back in 2021, one of these tests actually forced the astronauts aboard the International Space Station to shelter inside their return capsule in case they needed to evacuate ahead of the resulting debris cloud. Every single one of these tests adds permanently to the growing toll. The third driver might be the most insidious of the three because it's about pace rather than a single dramatic event. Debris is now being generated faster than nature's own cleanup process can remove it. Here's what that actually means. There's a natural cleaning mechanism at work in low Earth orbit. The extremely thin wisps of Earth's atmosphere that extend up to those altitudes create a tiny amount of drag, which very gradually slows debris down and drags it lower until it eventually re-enters and burns up completely. Think of it as the planet's built-in janitorial service, but that process is slow, and it only works efficiently at the lowest altitudes. Right now, we are generating brand new debris through collisions, explosions, and fresh launches faster than that natural drag can clear it away, so the running total just keeps climbing. It's a bathtub filling faster than it can possibly drain. All of this adds up to one striking statistic. In certain, especially busy bands of orbit, the rate at which satellite operators are receiving collision warnings, alerts that two objects might be on a crash course, is now somewhere between 5 and 10 times higher than it was just a decade ago. Operators are constantly forced into avoidance maneuvers, firing thrusters to dodge incoming debris, burning through precious fuel with every single maneuver, and quietly shortening the operational lifespan of their satellites in the process. Economists at the World Economic Forum have described this dynamic as a kind of hidden tax levied on every single space operation happening today. It rarely shows up as one dramatic, headline-grabbing catastrophe. Instead, it shows up as a slow, grinding erosion, higher insurance premiums, more fuel burn dodging debris, shorter satellite lifespans, and mounting friction for anyone trying to operate up there. It is, in a very real sense, death by 1,000 cuts, and those cuts are arriving faster with every passing year. Now let's talk about the true nightmare scenario, the one that genuinely keeps space scientists awake at night, because it actually has a name: Kessler syndrome. Back in 1978, a NASA scientist named Donald Kessler, working alongside a colleague, published a paper laying out a genuinely terrifying possibility. Imagine two large objects in orbit collide with one another. That collision shatters both of them into thousands of brand new fragments. Those fragments spread outward, raising the odds of yet more collisions happening. Each new collision spawns even more fragments, which in turn triggers still more collisions, and the cycle keeps feeding itself. It's a chain reaction, a cascade that, once it gains momentum, could become self-sustaining, generating more and more debris even if humanity stopped launching anything new starting tomorrow. And here's the genuinely frightening part of that scenario. If it ever played out fully, it could leave entire regions of orbit so saturated with debris that they become effectively unusable, too dangerous to fly through, too dangerous to place a satellite in. In the worst case, we could end up locking ourselves out of parts of space for generations to come. For a long time, this was treated as a purely theoretical concern, an unsettling thought experiment and nothing more. But as launch rates have surged and debris has continued piling up, it has started to feel a lot less theoretical and a lot more like a genuine approaching threat. Some researchers point out that the early warning signs of a cascade, rising collision rates, growing clusters of debris in specific bands, are already visible in the most congested corners of orbit. It's entirely possible we're watching the opening moves of the exact scenario Kessler warned us about almost 50 years ago. Let me pull this back down to Earth, quite literally, because none of this is purely abstract math. It's already producing real, tangible incidents. I already told you about the astronauts stranded by that cracked window back in 2025. But consider this too. The problem isn't even confined to space anymore. Back in 2024, a piece of debris that had come off the International Space Station actually survived its fiery plunge through the atmosphere and crashed straight through the roof of a home in Florida. Thankfully, no one inside was seriously hurt. But think about what that actually represents. Space junk is now, on rare occasions, literally falling out of the sky and striking the ground where people live their everyday lives. And as more objects continue launching, and more of that material eventually makes its way back down, the odds of these kinds of re-entry incidents will only continue climbing. So this isn't some distant, abstract problem playing out in a place disconnected from our daily lives. It is already reaching down and touching the surface of the planet directly. Now, I want to be completely fair and balanced here, because honest reporting means giving you the full picture, not just the frightening half of it. And the honest truth is that real progress is being made, and the overall situation is genuinely more nuanced than pure, unrelenting doom. That very same European Space Agency report that flagged the rising collision risk also documented real, measurable improvements in operator behavior. For instance, roughly 90% of rocket bodies currently in low Earth orbit now comply with the international guideline requiring objects to be removed from orbit within 25 years of their mission ending. And around 80% are meeting the European Space Agency's even stricter 5-year standard. That's meaningful progress. It shows an industry increasingly stepping up and designing its hardware to responsibly dispose of itself at the end of its working life. So this is not some hopeless, unstoppable death spiral where nobody is doing anything about it. It's a serious and genuinely worsening problem, but one that's running up against a growing, if still insufficient, effort to bring it under control. The real truth lives in that tension, genuine danger, genuine progress, and a still open question about whether that progress can outpace the danger in time. That's the accurate, complete picture, and it's the one you actually deserve. So why should any of this matter to you personally, someone living life down here on solid ground who probably has no plans of ever going to space yourself? Because you rely on that orbital infrastructure every single day, whether you've ever stopped to think about it or not. The satellites scattered through low Earth orbit and beyond form the invisible backbone holding up modern civilization. GPS navigation guiding your car and your phone. Weather forecasting warning entire regions ahead of dangerous storms. Global communications, television broadcasts, and increasingly internet access reaching remote corners of the world. The precise timing signals that synchronize financial transactions and keep power grids stable. Earth observation systems monitoring crops, tracking climate shifts, and watching for natural disasters. All of it runs through space, so if this debris problem were ever allowed to spiral completely out of control, if we lost safe, reliable access to key orbital regions, we wouldn't just lose a handful of expensive machines, we would lose pieces of the very infrastructure our entire modern world quietly depends on. That's what's genuinely at stake here. This isn't about protecting a few costly pieces of hardware. It's about safeguarding a system that billions of people rely on without ever realizing it. There's also a quieter casualty buried in all of this that's worth mentioning, the night sky itself, and the science of astronomy along with it. As tens of thousands of new satellites continue filling up low Earth orbit, they don't just raise the odds of collisions, They also reflect sunlight back down, appearing as bright, moving streaks cutting across the night sky. For astronomers trying to study distant corners of the universe, this has become a genuine headache. Bright satellite trails, photobomb telescope images, interfering with observations of far-off galaxies, asteroids, and countless other celestial objects. Some worry the sheer volume of satellites and debris could permanently alter humanity's view of the cosmos, dimming our connection to the dark, star-filled sky that every single generation before ours simply took for granted. It's a subtler kind of loss than a satellite collision, sure, but it belongs to the exact same story. The crowding of orbit carries consequences that ripple out into science, into culture, and even into the simple, universal experience of looking up at night. So what's actually being done about all of this beyond just improved disposal practices? Because there are people working hard on real solutions, and some of the approaches being developed are genuinely fascinating. The most direct strategy is known as active debris removal, physically going up into orbit and hauling the junk back out. Companies are now developing specialized servicer spacecraft capable of rendezvousing with a dead satellite, latching onto it, and dragging it down into the atmosphere where it burns up safely. One company based jointly in Japan and the United Kingdom has already successfully demonstrated the technology needed to capture and deorbit a target object. And a separate European effort already has a contract lined up to attempt its own cleanup mission in the near future. There are other creative ideas being explored too. Deploying drag sails on satellites, essentially parachute, like devices that catch those thin wisps of atmosphere and pull a satellite down faster once its working life ends. There's even experimental research into using ground-based lasers to gently nudge small fragments into lower orbits, where they'll decay and burn up naturally. Though that particular idea is politically delicate, since a ground-based laser capable of nudging a satellite could, under the wrong framing, look uncomfortably close to a weapon. But here's the catch, and it's a significant one. The economics simply don't work yet. A single debris removal mission can easily cost tens of millions of dollars, and right now there's no clear agreed-upon system for who's actually supposed to foot that bill. The debris itself is a shared problem. Everyone contributes a little to it, and everyone is threatened by it in turn. But that same shared nature means no single company or country feels a strong enough financial incentive to personally cover the enormous cost of cleaning it up. It's a textbook tragedy of the commons, a shared resource that everyone uses, but that no one is fully responsible for protecting. Until the economics shift, or until governments step in to fund and mandate cleanup efforts, the technology to solve this problem may well exist, while the money and the political will to deploy it at real scale still lag behind. And that brings us to the deepest layer of this whole problem, which ultimately comes down to governance and international cooperation. The foundational rules governing behavior in space trace back to a treaty signed in 1967, a period when only a couple of nations on Earth were even capable of reaching orbit at all. The world of space today, with thousands of satellites launched by dozens of countries and an ever-growing list of private companies, has completely outgrown that original framework. Experts increasingly argue that what's genuinely needed now is stronger international cooperation, mandatory and enforceable disposal requirements for everything sent into orbit, real, binding restrictions on those destructive anti-satellite weapons tests, and shared, coordinated tracking systems that let operators around the world work together to avoid collisions. The technical challenges here are genuinely hard, but the political and cooperative challenges may turn out to be even harder still. Space is, at its core, a global commons, and protecting it properly demands exactly the kind of coordinated international action that humanity has historically struggled to pull off. So here's the honest bottom line on all of this. The situation in Earth's orbit really is worse than most people realize. There are an estimated 140 million pieces of debris currently circling the planet, tens of thousands of them large enough to be genuinely catastrophic, and all of it moving fast enough that even the tiniest fragments are lethal on impact. The collision risk is climbing rapidly, up 20% in just 2 years, driven by exploding satellite counts, deliberate destruction from weapons testing, and a natural cleanup rate that simply can't keep pace. Real incidents are already unfolding, from stranded astronauts to debris crashing straight through a rooftop. And the long, feared nightmare of a runaway chain reaction, Kessler syndrome, has shifted from pure theory toward a genuine, if not yet fully realized, possibility. But, and this really does matter, it is not a hopeless situation. There is real, measurable progress happening around responsible behavior, real technology being actively developed to clean up the mess, and a growing wave of global awareness that something meaningful has to be done. The question that will define the coming decades is simply whether our efforts to protect orbit can outpace our ongoing ability to pollute it. The stakes could not be higher, because the invisible infrastructure circling above our heads is quietly holding up the entire world down here below it.